In this video, I'm going to formalize the reciprocal identities. I've been talking since I first defined the 6 trig functions that we had 3 pairs of reciprocals. Well, here it is in a formal identity form. Sine of theta is equal to the reciprocal of cosecant. And another way to write that is 1 over cosecant. Cosine of theta is reciprocal with secant, so we can say that cosine is equal to 1 over secant of theta. Tangent of theta is equal to 1 over cotangent. And then we can, kind of do the whole reciprocal thing with the other set as well. We can say that cosecant is equal to 1 over sine. Secant is equal to 1 over cosine. And cotangent is equal to 1 over tangent. I'd say in general, we usually use these 3 more when we're doing algebra things with trigonometric functions. That typically we like to change things into sine, cosine, and tangent if it's one of the other ones, and we use those 3 reciprocal identities to do that. So let's find cotangent if tangent of theta is equal to negative 1/5. Oh, we know that cotangent is the reciprocal of tangent. So that means we'll have 1 over negative 1/5. And we will multiply by the reciprocal of the second fraction and get cotangent to be equal to negative 5. Let's do another similar problem. We want to find secant of theta if cosine of theta is equal to the square root of 7 over 7. Well, secant of theta is going to be the reciprocal of that. I think it's easier to just think reciprocal and flip over the fraction than doing this whole 1 over business. We're going to get 7 over the square root of 7, which we then want to rationalize. It's going to give us 7 square root of 7 over 7. And then those 7's can simplify, and we're left with secant of theta being square root of 7. We can also use these reciprocal identities to help us solve equations. Here we have that secant of 2 theta plus 6 times cosine of 5 theta plus 3 is equal to 1. Now, we're going to talk about solving trig equations a lot later in the course. But in general, we always want our equations to have a single trig function in it if we can. Like, it's way harder to work with when you've got 2 different trig functions in the equation. So we want to try to transform it so it's just 1. I'm going to take this secant and I'm going to rewrite it as cosine. Using our reciprocal identity, secant of 2 theta plus 6 can be rewritten as 1 over cosine of 2 theta plus 6. And then that's still times cosine of 5 theta plus 3 equal to 1. And I'm going to put that over 1 and multiply straight across. This will give us cosine of 5 theta plus 3 over cosine of 2 theta plus 6 equal to 1. I'm going to multiply both sides by cosine of 2 theta plus 6 to get that out of the denominator. You could also think of it as cross multiplying. Either way, we'll get cosine of 5 theta plus 3 equal to cosine of 2 theta plus 6. We now have 1 cosine equal to 1 cosine. When this happens, we can just set the two arguments equal to each other. This is very similar to the one-to-one property when solving log equations. And now we'll just solve this linear equation for theta. Subtracting 2 theta from both sides. Subtracting 3 over. And dividing. We get theta equal to 1. Let's try another similar one. Now this one's a little bit different than the previous one. See, neither one of these to begin with were in the fraction form. In this next example, we have one in fraction form. I don't know about you, but I would always prefer to deal with something that's not a fraction. So I would definitely transform this one that was a fraction into the other trig function that isn't a fraction. Let's rewrite that right side as tangent of 5 theta minus 8. Since we know that tangent and cotangent are reciprocals, we can change it to the other function as long as we do the reciprocal. And now, 1 tangent equal to 1 tangent, we can just set these arguments equal to each other. Subtracting 3 theta from both sides. Adding 8. And dividing by 2. We get theta to be equal to 2.